It's only a couple minutes early. We'll go ahead and start. And we'll start by addressing your question here. Okay, call out the data to me. Texas. Okay, next. Oh, you don't have your book with you? $60. South Carolina had 35. Okay. Well, find the average or the mean. We're looking for the sum divided by the number. So that would be 355 plus 94 plus 34 plus 79 plus 27 plus 66 plus 39 plus 39 again plus 27 plus 22 plus 60 plus 35. That equals 877. Is that what you got? Divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For a mean of 73.08. But to the rounding, to the rules of rounding for probabilities, we carry it to one additional decimal place, which in this case would be 0.1. You add one significant digit when you're calculating a mean. Okay. That's the mean. So, what's the next step? We're calculating the variance. Right. So, 355 minus 73.1. Okay, 94 minus 73.1. You know what? Let's keep the extra significant digit. So we have 355 minus 73.1, 281.9. And 94 minus 73.1 20.9. Now, 73.1 minus 34 minus 73.1 is negative. Okay. 79 minus 73.1. $27. Okay, 66. $39. We're going to do that one twice. Now we got 27. We already did that once. I don't remember which one it is. Negative 46.1 and 22. Okay, now that leaves 60. And 35. All right. That is, now if you'll recall, there's a reason we square the variance. And that's because if we didn't, then the sum of the variance would just be 0. So let's do that as a check. Let's add these and see if they actually sum to 0. We got 281.9 plus 20.9 plus, minus 39.1 plus 5.9 minus, and the rest are all going to be minuses, 46.1 minus 7.1 minus 34.1 twice minus 46.1 minus 51.1 minus 13.1, and my phone won't let me go that far. Will yours let you finish? And it sums to 0. Did yours, did you get the same? You got 0. Okay, excellent. Then that's a pretty good indication that we're doing this right. So now let's take each of these terms and square them. 281.9 squared is no decimal points. Oh, okay. Well, that's good enough. And then the next one, squared 20.9. Minus 39.1 squared. I'm sorry, say that again. 39.1 squared. And what did you get? For 39.1 squared? Yeah, 39.1. 1,528.81. You said you got something different? Why did you? Oh, are you keeping a running sum? Oh, okay. That's no. I'm just taking the square of each term, and then then we'll add them up. And 5.9 squared. That means that would be 436.81. Seven nine. 467.81. You didn't keep the 0.9? Yeah, okay. All right. Let's keep going. 46.1 squared. $7.1 squared. Okay, 34.1 squared. $1,162.81. Okay, so we're going to repeat that. 46.1 squared is still 2125.21. 51.1 squared is 13.1 squared. And 38.1. Okay. Now let's take the sum of x minus x bar squared. And that gives us, we add all these together. Flood warning in this area. Okay. All right. 92,329.12. Is that what you got? Now, what do we divide that by? Well, there are 12 numbers there, right? 12 values in our sample. But because this is a sample, we divide not by n, but by n minus 1. So we've got the sum of x minus x bar squared divided by n minus 1 equals 92,329.12 divided by 11. And that gives us a variance of 8393.56. Two decimal places. What did the book say we should get? $83.93.5. Okay. And then that means the standard deviation is the square root of that. Which my phone isn't going to let me do. What's the square root of that? $91 and something. And is that what the book said it should be? And then lost place. 91.6. So, see how that worked now? Now, this is one of those things where you need to be careful and just, that's why I tried to pick problems with smaller data sets so you don't have to sit there going through 100 data. Excellent question. Why do we do minus 1 instead of divided by n? Yeah, I would have to look that up to be able to quote it accurately. But forget about quoting the book right now. Let's try to understand why that is. The better way of asking the question is, okay, the short answer is you divide by n minus 1 instead of n because the sample standard deviation will always under-reflect. It will underestimate the population standard deviation. Okay, now recall, we're dealing with parameters, which are measures of, in this case, variation of a population of data distribution. When you're dealing with the whole population, you're dealing with parameters. When you're dealing with a sample of the population, then you're dealing with statistics. Okay? And the statistic always underestimates the parameter. If you calculate the standard deviation for the whole population, it's always going to be a little bigger than if you calculate the standard deviation for just a sample. Now, to understand why, that's what you need to understand the why of. Why does it always underestimate? why, in other words, would it not be true that if you're taking a randomly selected sample, why wouldn't the standard deviation of that sample be just as likely to overestimate the standard deviation or variance as it is to underestimate? Well, consider the range of the population. Okay? The range of the population is the largest number, the largest valued datum, and minus the smallest valued datum. So, now think about the range of a sample of that population. It is mathematically impossible for the range of the sample to exceed the range, to be greater than the range of the population. It will always be smaller. Mathematically, it's possible, and this is getting into today's chapter if we still have time for it, but there is always going to be there's a finite probability that you might just randomly pick the largest data value and the smallest data value in your random sampling. Depending on how big the population is, it's pretty unlikely. So, the reality is that your range of your sample is always going to be smaller than the range of the whole population. Now, what about the variance? How do you calculate the variance? The variance of each member is going to be either greater than or less than the mean, but you always square them, making them always much greater than the mean. And because you always square them, you make them bigger. So no matter how you select your sample, it's always going to be a little less than the variance of your sample is always going to be a little less than the variance of the population. There is no opportunity for it to be a little, there's no opportunity for it to go, a little bit more or a little bit less. It will always be a little bit less. Empirically, we have determined that if you subtract 1 from the n, when you do the division, what that does is it artificially raises the variance and subsequently the standard deviation of the sample. And it's an artifice. It artificially makes it a little bit bigger than it would have been if you just calculated it normally by the definition. And that's the whole point. It makes it a little bigger, which makes it a more accurate estimate of what the population variance would be if you calculated the whole population. Okay? Do you understand the why of it now? Yeah. And it does all stem also from the fact that your sample is never going to exactly reflect the population. Just never going to happen. And so what you have to do is, when you start doing inferential statistics to try and make estimates of the, estimations and predictions about the population as a whole, you're really dealing with probabilities at that point. And in fact, that's the whole point of chapter 3 that we're going into right now. Because we got to cover some chapter today. That said, I do want to make sure you understand you can come by my office during my office hours, and I will work with you to help you get caught up. Now, chapter 4 we're going into now is on probability and counting rules. And in point of fact, as I just said, the the whole purpose of inferential statistics is to make guesses or estimations of about entire populations based on statistical analyses of small samples of subsets of that population. The whole basis of doing this is the idea of probability. Okay? When we're doing statistical analyses, we are never going to be doing exact measurements. We're never going to be talking, even when you do exact measurements, you always have an uncertainty. Okay? You can't measure a length to an absolute precision. You can only measure it to the precision of the instrument that you're measuring it with. Well, in the case of statistical analysis, that uncertainty stems not from the precision of the instrument, but from the probabilities involved in the calculations. And so when we will see later on in the semester, when we start talking about drawing inferences on about populations and stating hypotheses and testing those hypotheses, it will be based on the probability of a particular statement being true or false. And that means we need to have some basic concepts about probabilities. A probability experiment is a chance process that leads to a well-defined result. That result is called an outcome. Okay? So, what would a chance process be? Tossing a coin, rolling a die, drawing a card. In fact, probability theories evolved out of games of chance, of cards. As a physicist, there's a whole other depth of understanding and philosophy that we're not going to get into about the idea of what people call randomness. Okay. In fact, we live in a universe that is relentlessly dictated and governed by causality. Okay? So the fact is, nothing happens by random chance. Everything happens by cause. Something causes it. Okay? Everything, all processes, flipping a coin, we call it random because we can't predict the outcome. But in point of fact, there's nothing random about it. The moment that coin leaves your thumbnail and it's flipping through the air, the outcome of that coin toss is fully determined the moment it leaves your thumbnail. It leaves with a certain angular momentum and a certain velocity trajectory through an atmosphere of a certain density to a floor a certain distance below. And now, the outcome is so hypersensitive to all of those little variations in its initial conditions that we simply can't predict it. And so we developed mathematics to deal with that called probabilities. Now, the outcome is the result of a probability or a chance experiment. You also need to know what the sample space is. The sample space is the sum of all possible outcomes. All right? You toss a coin. How many possible outcomes are there? 2. Because is it possible that the coin might land on its edge? Not really. I mean, you can stand a coin on its edge. Unless you're writing a script for a Hollywood movie, it's not going to happen. It's either going to land heads or it's going to land tails. So what is the sample space for a coin toss? Two. There are two possible outcomes. The outcomes are either H for heads or T for tails. If you're rolling a die, a single die, what are the possible outcomes? 1, 2, 3, 4, 5, or 6. There's a sample space of 6 possible outcomes. Every roll of the die will be one of those 6 outcomes. Unless you paint dots on a little white marble, in which case, at that point it's no longer a die. What if we toss 2 coins? Now what does the sample space look like? What other possible outcomes are there? That one could be heads, and the second one could be tails. That one could be tails, and that one could be heads. There are 4 possible outcomes, so it has a sample space of 4. Here on page 195 of your book, in example 4.1, it shows the sample space of rolling a pair of dice. Each die can land on 1 through 6, and for each outcome of the first die, there are 6 possible outcomes for the second die, giving you a total sample space of 36 possible outcomes. Example 4.2, find the sample space for drawing 1 card from an ordinary deck of cards. How many cards are there in a deck? And there are 52 possible outcomes from drawing a single card from a deck of cards. The sample space then of drawing a single card from a deck, 52 possible outcomes. Now let's look at one that gets a little more complicated. Find the sample space for the gender of the children if a family has 3 children. Well, it's possible that all 3 kids will be a boy. Child 1, child 2, and child 3. It's possible that the first 2 will be boys, and the third one will be a girl. It's possible that the first one will be a boy, the second one will be a girl, and the third one will be a boy. It's possible that the first one will be a boy, and the next 2 will both be girls. It's possible that the first one will be a girl, followed by 2 boys. And then it's possible for girl, boy, girl, 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 boy, and girl, girl, girl. What is the sample space? Eight of them. Now, recognize the pattern of the progression of permutations? What is it? Come on, you're my IT guy. Recognize it? It's just counting in binary.
0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1.
1, 2, 3, 4, 5, 6, 7. Starting at 0. In the case of the book, they want to show you how to find this by doing a tree. Tree diagram. Okay. Look at how we get there. We start at 0. And there are 2 possible outcomes for the first child. Boy and girl. Now, what about the second child? Well, from this one, you can have a boy or a girl. And from this one, you can have a boy or a girl. Boy, girl, boy, girl, boy, girl, boy, girl. Everybody see how this works? For each layer of the tree, you have however many possible outcomes from each of the initial possible outcomes. Now, since they're all 2, what is 0, you have 2 possible outcomes, or 2 to the power of 1. But now if you multiply those 2 by 2 each, you get 2 squared, or 4. And if you multiply each of those outcomes by 2, you get 2 cubed, or 8. Now that works out, it works out nice in this case because 2 is a number that we're accustomed to using as a base. But what if the possible outcomes were 6? Like the chance that you can have 6 outcomes on a roll of the die. So what would the chance? What then is the sample space? Here you start the sample space of 1 child, 2 to the power of 1. 2. You roll 1 die, there's 6 possible outcomes. 6 to the power of 1, 6. What if you rolled 2 die? No, 6 squared. 6 to the power of 2 is 36. And if you'll back up 1 page, you'll see where we passed right over that one. Example 4.1, rolling 2 die. You can roll 1 of 6 outcomes. For the first one, and then you can roll 6 possible outcomes off of each one of those. So here you got 6 to 1, here you got 6 to the power 2. If you were rolling 3 dice, if you were rolling Yahtzee, 6 die, what's 6 to the power of 6? 6 to the power of 6 is a big number that I don't want to try and calculate in my head, but that brings us to classical probability. Now, what is the basis of classical probability? In classical probability, we assume, catch up with me, little screen, thank you. In classical probability, we assume that every possible outcome has an equal probability of occurring. Okay, we're assuming here that for every child they have, there is an equal probability that it will be either a boy or a girl. We are assuming that every time we flip the coin, it has an equal probability of landing heads or tails. And so the probability of it landing heads is 1 in 2. Here we have the formula for calculating classical probabilities based on equally probable outcomes or equally likely events. And the probability of any event E is calculated as number of outcomes in E divided by the number of outcomes in the sample space. In this case, what is the probability of having 2 boys and 1 girl? There's 1, there's 1, there's 1. That's it. The probability of having 2 boys and 1 girl is 3 in 8. There are 3 outcomes that would fit in that would describe that with 3 possible outcomes that would out of that sample space. So it's 3/8, which you can punch the numbers into your calculator to turn that into a decimal. You'll notice that there is also 3 in 8 chances that you will have 2 girls and 1 boy. 1, 2, and 3. So there. Chances of having 2 boys and 1 girl. What are the chances of having 1 boy and 2 girls? Well, we've already calculated that. What are the other possible outcomes? All boys and all girls. 1 each. What's the sum of all possible outcomes? 8 out of 8. 3 plus 3 is 6, plus 1 is 7, plus 1 is 8. You're also going to find that probabilities are generally expressed as either fractions or as decimals. And the standard rule of thumb is that you will use 3 decimal places. In baseball, they call it batting 300. That means you're going to hit 300 times out of every 1,000 that you at bats. Drawing cards. Probability rules. Probability of any event E is a number, either a fraction or a decimal, between and including 0 and 1. The sum of all probabilities will equal 1. If E is not a possible outcome, what is the probability of E? If the sample space is 8, what is the probability that one of the children in this family will be a dachshund? 0. So the probability of being a dachshund is 0 divided by 8 is 0. If an outcome is not possible, its probability is 0. What is the probability that the 3 children will all be either boys or girls? It will be 8 out of 8, which is 1. So if an outcome is a mathematical certainty, its probability is 1, unity. If it's not possible, its probability is 0. Now, there's something here called complementary events. Basically, if the event set is E, then the complement of E is every outcome that is not E. Okay? So, in this case, we looked at the outcome be what is the probability of having 2 boys and 1 girl. And we found that the probability of E, where E is 2 boys and 1 girl, was 3 out of 8. E bar is any outcome that is not exactly 2 boys and 1 girl. So E bar would be either 2 girls and 1 boy, or 3 girls, or 3 boys. So that means the probability of E bar is going to be 3 out of 8 plus 1 out of 8 plus 1 out of 8 is 5 out of 8. Now, the probability of E is 3 out of 8 in this case. The complement of that, E is not E. The probability of the complement of E is 5 out of 8. But notice that in every case, the sum of any probability and its complement must always equal 1. Now, I got time to cover this. This has all been based on classical probability. Right? So, what is the alternative to classical probability? What's the basis of classical probability? The assumption that every outcome has an equal likelihood. Every possible outcome is equally likely. That's the basis of classical probability. What then is the basis of empirical probability? That every outcome is not equally likely. You might assume that a coin is fair, or that a die is fair. And so there is an equal chance that you're going to roll a 6 as a 1, as a 2, as a 3, as a 4, as a 5. But what if the die is loaded? Now, if they can do that, more power to them. Yeah. But what if the die is loaded? So it doesn't have anything to do with the technique of the person rolling it. If the die is weighted on one side, then it is going to have a higher probability of rolling the number opposite the weighted side. Pit bosses in Vegas and the various casinos around the country, they spend a lot of time looking and analyzing the die that are being rolled on the crap table. And if they notice that the outcomes are varying too greatly from what they would expect, they conclude something's not right with that die. Now, maybe it was, maybe someone slipped a loaded die into the set. Maybe it was just a manufacturing flaw. They don't know or care why it's not fair, why it's not equally probable, but once it becomes empirically evident that that the die is not obeying what's called the law of large numbers, they get rid of that die and put in a new one. Another good example of using, and this is why we will use a lot of empirical probabilities in this course. What if someone from the AAA, the example in the book, someone from the Automobile Association decides they want to find out how people are traveling for the holidays? They do a survey. Would you expect that that it would be equally likely to choose to drive or to fly? Or would you expect that there would probably be a greater probability that one or the other is chosen? Point is, there is absolutely no reason to expect that they're going to be equally probable. So you do a survey and you establish a frequency distribution, and you find out empirically what are the associated probabilities. And then that's what you use for making your calculations and inferences. Couple of minutes left, so I want to cover 3 points real quickly. How many of you have heard of the law of large numbers? Okay. Do you believe that if you flip a coin, there's a 50-50 chance it'll land heads or tails? It's equally likely to land one or the other. So if you flip it 10 times, are you going to get 5 heads and 5 tails? No. You're not going to get exactly 5 and 5. You're going to get something smaller. But as you flip it more and more times, you flip it 100 times. Okay, if you flip it 10 times, you might get maybe 7 of one and 3 of the other. But if you flip it 100 times, it's not very probable that you're going to get 70 of one and 30 of the other. More likely you'll get 40-something of one and 50-something of the other. But you're still not going to get exactly 50 and 50. You get to 1,000 times, now you might be closer to 48 of one, 480 of one and 520 of the other. Or 490 of one and 510 of the other. The larger the number of in your sample set, the larger the number of experiments, the closer your empirical probabilities will approach your classical probability. Okay, but they're never going to, in order to get there, you would have to do the test an infinite number of times. Eventually, you might just happen to hit it for one trial. On one trial, you just happen to get, oh, look, if we round to 3 digits, then we're there, 50-50. Well, this is the law of large numbers. And people make a mistake when they think that because the classical probability is such, then the numbers should even out. This is why when we take samples, they never ever actually match the population. And when you then add in the fact that, by the way, this is an important point. Because I don't know if you remember this, if you were here for this. The fact that the sample will never exactly match the population, the fact that the statistic will never exactly equal the parameter, that is called sample bias. Okay? A sample bias is not an error caused by the person doing the sampling. The sample bias is simply the fact that the sample will not match, ever. When the person doing the sampling throws in an additional error, that's called non-sampling bias. And the fact is, the sample bias is simply a statement of the fact that we understand the sample is going to have a bias built into it. You can read subjective probabilities and risk-taking. Subjective probability simply means that the person who has expertise and experience draws on it to make a guess as to what a probability would be based on their expertise. Whereas subjective probabilities can be valid and good and accurate, and sometimes not so much. In fact, if you take and base your subjective probabilities based on a sample of people and what they expect the probability to be, you would find out that a lot of times that those guesstimates will be very wrong. You'll read about that in the book. And I'm going to have to stop there because we're out of time. We'll try to get through the rest of this chapter on Friday. We have an exam at the end of next week that will cover chapters 3, 4, and 5. And since we lost a day this week to a holiday, if I am going to end up being behind, we may make that exam a take-home exam, just to try and catch back up to the schedule. If we can cover the rest of the material in time, then we'll do it in class. Any questions? Other than, can I shut up and let y'all leave? Yes. Yes, I can.